Alright, so today we're going to be taking a look at more polynomial functions and looking at the key features of graphs and tables of these functions so that we can kind of learn more about the situation that we're working with. So to get us started here, the graph below represents the rate at which people enter a local amusement park in hundreds of people per hour after 12 p.m. or noon. Two questions are, the park has a promotional event from 6 p.m. to 9 p.m. where they offer half-price admission. Did the promotional event work? And explain your reasoning. And then secondly, what is happening before t equals 2? And explain that in the context of the problem. So go ahead and copy this down, copy the graph down, and answer both of these questions. And in doing so, notice what different pieces of the graph you used and what they meant. Okay, so the promotional event from 6 p.m. to 9 p.m., the first thing you want to do is locate on the graph where this is. And since 0 is noon, 6 p.m. is going to be right here, and 9 p.m. is going to be right here. So if we take a look, what happened during that, on that interval from 6 p.m. to 9 p.m., and I use the word interval to talk about everything in between 6 and 9 p.m., and if you look, you can see that the rate at which people were entering was increasing between 6 and 9 p.m. So you could say, yes, it was working because the rate at which people entered increased over that interval. You could also talk about how at 6 p.m. it was, about 150 people per hour, and you might have assumed it would only continue moving downward if there was no promotional event, just like it does after the promotional event ends. But instead, it actually returned and started increasing again and reached 300 people per hour, what looks like right before 9 p.m., and then started decreasing again. So you want to note, look, there was a minimum-ish value. We'll talk a little bit about what this means later on. But there was a kind of a drop and then an increase again between 6 and 9 p.m. What is happening before t equals 2? So if you notice, at t equals 2, what is this? This is a root, right? A 0, where the function intersects the x-axis, which means that the y value is 0. And so before this, it would seem like the entrance rate would be negative. But that doesn't really quite make sense. So how do we interpret this in the context of the situation? Well, think about the amusement park. If there's no one entering the amusement park, what do you think that means? Probably means that it's closed, right? So what you might say is before t equals 2, the amusement park was closed, meaning that the amusement park doesn't open until 2 hours after noon, which would be 2 p.m. So the big picture here is that we're using the key characteristics we've talked about before, notably the roots, to make some sense of some situations. And we're also looking at how the function behaves, which is another key characteristic, right? Is the function increasing? What does that mean? Maybe it's decreasing as it is here. What does that mean? Maybe it's at its maximum value. What does that mean? And these are all going to help us understand the situation even better. All right, so there are a couple key points that we want to make sure we understand and get down. The first is that functions have multiple representations. So we just saw a graphical representation. We're probably pretty used to looking at equations and looking at graphs. But we're going to look a lot more at tables in this unit because a lot of the time when you collect data, you're actually going to be logging it in a table. And so you want to be able to think about how those table of values relate to the function and how it can help you make sense of the real-world situations you're working with. But the really important part is that we can use the key characteristics of functions to discover important information about a situation, regardless of whether we're working with tables, graphs, or equations. And so just to remind ourselves of what these key characteristics are, right? There are, of course, the roots or zeros of a function, also known as the x-intercepts. We have what we've been used to calling the vertex, and when we see some of these functions like the one that you just saw, you'll notice that there are what appears to be multiple vertices, right? So what I'll say are vertices, plural, and what this tells us, right, we're thinking max/min values. we have the y-intercept. And there are a couple of more key characteristics that we're going to look at as we looked at in the first example, which are where is the function increasing, where is it decreasing, increasing/decreasing. And going along the same lines, where is it positive and where is it negative? As we saw in the last situation, we were looking at the roots, and we noticed, well, if the the number of people that are entering is negative, that doesn't make a whole lot of sense. And so what we can think about is, what does that mean in the context of the situation? That probably means that the amusement park is closed. So these key characteristics are going to help us understand situations, whether they're represented with an equation, with a table, or with a graph. So we'll get some more practice. We're going to do a very cool task in class where we're using a table to take a look at a given situation. But in order to get some practice with that, I want you to go ahead and try this problem. All right, so here's a problem for you to try. And notice here that we have a table instead of a graphical representation of the function. So the velocity of a subway train as it leaves the station is given by the function v, shown in the table below, and the interval where t is greater than or equal to 0, or less than or equal to 200. The questions are, what time does the train arrive at the next station? Explain. And B, what was the average rate of change of the velocity of the train from 20 seconds to 80 seconds? And what do you think this means in the context of the question? There's a couple of things going on here. So first, go ahead and copy it down, give it a try yourself, and then once you've tried it, go ahead and press play again. I'll talk about it briefly to hopefully give you a few more hints as to how you can move forward and answer both questions. All right, so a few things to note here. The first is what the table is telling you, and so it tells you at a certain number of seconds what the velocity of the train is. And you are familiar with velocity because every day when you get in the car or the bus or whatever it is, you're traveling at a certain velocity, right? Maybe 30 miles per hour, maybe 50 miles per hour. And so you should have a good understanding of what that means. As you might notice, this subway train doesn't travel in miles per hour, but meters per second. So 20 seconds in, the train is traveling at 3 meters per second. 80 seconds in, it's traveling at 9 meters per second. So you can think about what that means in context, and when answering the question, what time does the train arrive at the next station, you can look at the table and think about what is it that you're actually looking for. What will it mean in terms of the velocity? What will it mean the velocity of the train will need to be when it has arrived at the next station? For part B, what was the average rate of change? Well, what you want to think about here is, on average, how much was the velocity changing between 20 seconds and 80 seconds? I'll leave it at that, and I want you to experiment with it a little bit and have an answer for B that makes the most sense to you. Maybe it won't be right, but as long as it makes sense to you, it will eventually be able to get to the correct answer.